Hi everyone, welcome to 3 Deviations. I'm Stuart Christensen, and today we are going to begin our course on multivariable calculus. Now, if you are coming off of the single variable calculus playlist, you will have noticed that I said at the beginning of the last unit that the parametric and polar curves unit is really a primer unit for multivariable, and that is true. We are going to be parameterizing everything when we're dealing with vectors, and also the polar coordinates are going to be especially important when we're dealing with integrals. Now, I'll just start with a general introduction to the course. So what we're going to be covering is we're going to start by covering the two other kind of primer units, which are going to be three-dimensional space, which we're starting today. Then we're also going to cover vector functions, which we'll start later on. And both of these units are meant to give us the tools that we will need to cover the other three units of multivariable calculus, which are very important. So those other three units will be partial derivatives, so derivatives of multivariable functions, multivariable integrals, which will be integrals of multivariable functions, and then vector calculus, which will be derivatives and integrals of vector calculus. And vector calculus is really the capstone of calculus. It's the most applicable because A, it deals with vectors, which are very natural quantities, and also it deals with three-dimensional space. And three-dimensional space is the space that we live in. So it's very important that we deal with three-dimensional space because that's the world we live in, and that's what we really want to model. Calculus 1 and 2 are very helpful in developing these skills, but now we can actually use these skills to real-world applications, maybe not just modeling motion or something like that. Now we'll be able to model things a lot more in a nuanced way. Anyways, now we can begin talking about three-dimensional space. Just to note, this video will seem fairly trivial despite the obscure notation I've used. But let's start. So here's a definition for three-dimensional space. So we take the Cartesian product of the real numbers. We take r times r times r. Now what does this mean? So this means that I'm taking a real number line, taking all of the real numbers, and then I'm adding another real numbers. So now we've got real numbers squared, so r2. And this gives us an xy plane, and then we add r3, which gives us depth, and that gives us space. So this Cartesian product can be defined as an ordered pair of x, y, and z, such that x, y, and z are in the real numbers. So this obviously yields a point given an x component, which is this axis, a y component, which is this axis, and a z component, which is this axis, which gives us roughly, we've got over here and over there. Let me go up z amount. That gives us roughly this point. So that's our point P, given that initial set. All right. So that is the Cartesian product and three-dimensional space. It should seem fairly easy. Anybody who's watched my other videos will know that I'm a horrible drawer. I cannot draw even two-dimensional images very well. So it'll be quite an adventure to see how well I can draw three-dimensional images. We might need to bring in some pictures when we start dealing with more nuanced functions. Anyways, now we can start talking about some more interesting things. So I want to discuss representations. How can we represent the three-dimensional space? Now, in the last unit of single variable calculus, I discussed how we can model two-dimensional space either with a Cartesian representation or a rectangular representation. So that used an x-axis and a y-axis, which looked kind of like that. So we have an x-axis here, the y-axis here, and with any x and y can model any point on that plane. But we also discussed how we can use a polar system. So we have a radial axis, so the polar axis we usually call it. And we also have a sweeping angle, which we call theta. So that's our sweeping angle theta. And that could also sweep out the plane with any combination of r and theta. We could get any value that we could get with the with the Cartesian representation. So we have two complete representations for two-dimensional space. Now we also need to discuss three-dimensional space. Now two of these are going to seem fairly trivial extensions, and then we have a third one that we can use. Now most of these are not going to be particularly important until we get into integration, because sometimes when we switch coordinate systems, it can become easier to integrate functions. But we will discuss now all of the three, but we will be using rectangular the most. So we have the rectangular system, so we have an x-axis, or actually, I'm drawing this wrong, and it's fine. So this is our x-axis, this is our y-axis, this is our z-axis. So as you see, in the xy coordinate plane, we have quadrants. So we have quadrant 1, we have quadrant 2, we have quadrant 3, we have quadrant 4. Well, in the 3D coordinate system, we have octants because we have 4 quadrants on the top and 4 quadrants on the bottom. So we've got octants, so that's another way to represent it. But anyways, with rectangular system, we have a coordinate pair, an ordered pair, an x component, a y component, and a z component, which can create a point. Likewise, we can have a cylindrical system. Now, the cylindrical system is really an analog to polar. It takes this up here and really generalizes it by just adding a z-axis. So we can take the polar circle and turn it into a cylinder by giving it a height. So we have, I'll try to draw this. So we have a z-axis, we have a polar axis, and then we have a sweeping angle. Draw this as an ellipse, maybe that will be good. Then we have up here our sweeping angle theta. And then to give it height, we have z. So this generates a cylinder. And this is also a complete representation of 3D space. Now finally, this one might be more of a new thing for you, but we also have a spherical representation. Now a spherical representation kind of does away with all of that other stuff. Probably shouldn't have drawn that line. Actually, yeah, let's restart. So we're going to get rid of this line here. We don't want that anymore. We still have our radial axis. And this gives us magnitude. So r gives us magnitude. Now we also have that same angle that can give us sweeping across the xy plane, across the horizontal plane. We call that theta. But then we also have, let's say I want to represent this point here, I might need to go over theta. But then I also might need to go up some angle phi. So phi is the angle that controls the height. So looking at it from the top, from a bird's eye view, we just see a circle. We have a radius, some r, and then some theta away from the polar axis. And then looking at it from the other side, we have, or this would be this would be a horizontal component of r. And then looking at it from the other side, we have a vertical component of r, some sort of vertical component of r, and then an angle phi away from the horizontal. So it's a little bit complicated, the spherical system, but essentially think about it as a sphere around the origin, and using any point, using its longitudinal and longitudinal angles, as well as its magnitude, to describe how far away it is. Now, that was a really bad explanation, but the important thing is the spherical system is also a complete way of describing the three-dimensional space. Now, interestingly, we use spherical coordinates without the theta, or without the r, only with theta and phi for latitude and longitude here on Earth, because obviously our radius is constant, I guess with the exception of mountains, but that's really negligible, and we can probably not regard that as significant. But those are three ways that we can represent our 3D space. I would really pay attention to rectangular for now. All right, enough of that. Now I'd like to discuss distances. This is something you probably learned in Algebra 1. I'll go over it really quickly, but in a more general way. Here I'm using a summation convention such that it's implied that I is summed over. So in the general case, to find a distance, the magnitude between points P and R, I take the square root of R sub I minus P sub I. So that's the distance between any two components, and then I square that, then I sum over the i's. So in the three-dimensional case, I takes the value of x, y, and z. So I'll put a little circle up there. So in the three-dimensional case, we get the magnitude between P and R, so the distance between P and R is equal to r sub x minus P sub x squared plus r sub y minus P sub y squared plus r sub z minus P sub z squared. Sorry, we should have a squared there. Anyway, so that's the distance for 2 points in three-dimensional case, and this works for n-dimensional cases. All right, now we will discuss one last thing before we shove off. We'll discuss spheres. So if we have a sphere centered at the point HKL, then the formula for the sphere is going to be x minus h squared plus y minus k squared plus c minus l squared equals r squared. So given that we have a radius of r. Now this should be very trivial. This is an extension of the equation for a circle that, again, you probably learned in Algebra 1 or Algebra 2. And that is a sphere. All right. So I would also like to mention that these rules are very trivial, but they're very important. So it's just good that we get these down. And all of the rules and additional algebraic things or geometric things that you've discussed in your first year algebra course or second year algebra course do apply to 3 dimensions. All right, thanks for watching our first video for multivariable calculus. In the next video, we are going to introduce the notion of a vector, maybe something you've seen in physics. Again, Unit 1 here is going to be very algebraic. We're not going to have much calculus, but it's an extremely important foundation that we need to set in as soon as possible. All right, thanks for watching, and we'll see you next time.